Good morning and welcome to the next lecture on big data. In the last lecture, we finished a chapter on big data, small data, all data. In particular, we looked into data quality, biases in data sets, and small sample size problems. And you had a homework to read about machine learning operations. Anyone has looked into those references? It's certainly very helpful for you with regards to the seminar topics. I'll talk about the seminar presentations later, but today we will continue with the content. First of all, we'll be looking into uncertainty in learning. Concretely, we will discuss a bit about confidence intervals and statistical tests. We'll look at Gaussian processes and then in detail into an approach that is called conformal prediction, and then into a different technique that we call model calibration. Just before this lecture, there was actually this AI project discussion, and some of you take this project with me, and there was a discussion about label errors in one of the groups, and there were some mini presentations. So label errors also contribute to uncertainty in learning, because if in your training set some of the labels are incorrect, you're learning a wrong pattern. That's something we're not discussing in this lecture, but we will look into a few other problems around uncertainty in learning. It's a new chapter. If you look into last year's recordings, you don't see this chapter. I've added it this year. Maybe next year, I'll also add label errors as another uncertainty, but we'll start with these topics this year. So when you train your machine learning model and you want to evaluate it, so you want to evaluate the hypothesis, there are many things you can do. So typically you would start training your model on a training set with a test set in order to assess how good or bad the model is. And if you want to choose among multiple models or candidate models, you would also introduce a validation set in between. That's what you typically do, but then you want to assess the model. And what you often say in classification would compute is a confusion matrix. And in classification, you can compute all sorts of metrics from the confusion matrix in order to assess how well your model does in classification. For example, accuracy, precision, recall, or F1. Area under the receiver operating curve is also something. If you look at regression, there are other metrics. For example, R2, you could also compute errors like a mean squared error or something. So these are all the things you can do, and then you can still do cross-validation if you want. But eventually, that's not enough. A lot can actually go wrong. We've seen in the data quality chapter before, we've looked into class imbalance, which has impact on classification performance. You may actually have a model that has a super high accuracy, yet it doesn't work useful at all because your data set is highly imbalanced. You have all sorts of other biases like covariate shift and so forth. And there was also this survey paper that I linked about impact of biases in big data that you should definitely read if you haven't read it yet. But it's still not that easy. For example, if you train a regression model and you make predictions, probably all predictions you're making are wrong. Because with a classification, it's somewhat easier. You have a classification, you have two classes. It's discrete, but if you have a continuous label that you want to predict, probably all the labels you're predicting are wrong in some sense. Maybe a little bit off, totally off, but it's unlikely if you have a sufficiently large interval in which you want to predict that you're always predicting correctly with a continuous variable. So we also need to be thinking about that. Actually, maybe we don't want to just predict a certain regression value. Rather, we maybe want to have some interval or some confidence measure or something. And there, if you look, for example, at classification, there are lots of other questions we can ask ourselves. For example, you can observe the accuracy of certain models, and you have a limited sample of data to make such comparisons. How well does that model actually perform over additional examples that we have not seen yet? We could also wonder, we have one model that outperforms another one on a certain data set. How likely is it that that model also performs better on another data set? We just add a little bit more data to the test. Does that model still work better or not? Our data is always limited, and what can we do to take advantage of this data to both learn a model as well as estimate its accuracy? So these are certain questions that you will come across in the real world, because it's unlikely you're just building a classifier on some data set which totally represents your customers and you just predict 0, 1. Maybe there's far more data coming in that you cannot use in your training yet. Maybe you want to do regression, and all the regression values you're predicting are probably wrong to some extent. There is methodology that we need in order to address these questions. And these 3 questions are actually something that is not new at all. This was already discussed in the machine learning literature in the 1990s. But I guess you have not seen these questions in a machine learning course so far, I guess, right? And there's actually a very good book on machine learning from the 1990s. It's called Machine Learning by Mitchell. Has any one of you used this book for studying machine learning? It's a classic machine learning book. It's not outdated at all yet. Obviously, there's no deep learning in it, but I think it was one of the early comprehensive machine learning books. And the beauty of that book is it not just discusses what's a decision tree, what's a neural network, but it also addresses a chapter that I have not found to that extent again in the literature that's called evaluating hypothesis, which is more than just, calculating a confusion matrix and then computing an accuracy, but rather addressing these questions. And in order to address these questions, we need to look into confidence intervals and statistical tests. This is something you have learned in your statistics course, at least to some extent. And in order to address these questions, we need in particular paired 2-sample t-tests. Anyone still remembers the t-test? Okay, then there's a paired 2-sample t-test. And that one is particularly useful to compare the performance of 2 classifiers. So you can say which classifier is really better than the other one, taking these questions into account. That's your homework for next week. Read this one book chapter, Evaluating Hypothesis, because if I try to revise from scratch what are confidence intervals or paired 2-sample t-tests, some of you know it very well, some probably not anymore. And because this is so explained so well in this book chapter, take a look into the book chapter. The book is easy to access online. And if you don't have this book, maybe buy it. It's probably one of the most useful machine learning books ever. I used this a lot when I studied AI, which was far after the late 90s, by the way. So the book looks old, but it's still useful. So this is covered extremely well in that chapter. So I felt it doesn't make much sense to discuss the chapter here. This is rather your homework for next week, because next week we're not meeting because you have 2 tasks until the session in 2 weeks. Next week, your task is read this book chapter and also think about a seminar topic. Who of you has already thought about a seminar topic? Yeah, then I'll say something about the seminars now before we dig deeper into uncertainty in learning, because after this, we'll look into Gaussian processes, conformal prediction, and model calibration. So we'll go back to the introductory chapter. The seminar presentations are the thing you get examined on in this course. We are using a book that appeared maybe 2 years ago or something like this. It's called Machine Learning Design Patterns. You all learn about design patterns in a software engineering class, like composite, strategy, and all these ones. They're super helpful for software engineering, but for machine learning, also some best practices have been established over the years. There's a book written by 3 senior engineers from Google, and they present in detail how they approach machine learning at Google and which best practices they have developed over the years. There are 30 design patterns in it, and you can apply them to far more problems outside Google, by the way. And your task is, you need to find a seminar topic. When I created these slides, I said early May, but now we're already mid of April, so a bit earlier, but some of you asked me recently when you can pick your seminar topic. That's why this is now a bit earlier. And if you check the iLearn course, you can pick your seminar topic. This will only open at 1 p.m. because I want you to be able to follow this lecture. And you will pick one of those 30 design patterns. The book is also available as an ebook through our library, so you can access it for free. And you will pick one of the design patterns, and you will be in groups of 3 to 4 students. And I'm getting a lot of emails if I do exceptions about 2 or 5 students. I don't, so it's 3 to 4 students. And you would pick your design pattern in this iLearn section. So you don't see this yet. It will open in iLearn at 1 p.m. It's like a free choice of a group. And there are groups 1 to 30, where 1 stands for design pattern 1, 2 for design pattern 2, and so forth. And you can add yourself to a group. What you need to do is, because of I only see your name when you join the group, but you can add a comment to the group, and you also need to put in your student IDs, because I need the student IDs to put in your mark eventually. So everyone has to join that group, because that group needs to be 3 to 4 students. Otherwise, it's an invalid group. And then once you have finalized your group, also one of you just amends the comment of the group and puts a link between name and student ID. Otherwise, I'm unable to put in your marks in the system. Then you've seen the date for the seminar presentations. It's sometimes at the end of the term. And your seminar presentation will take 15 minutes together for those 3 to 4 students. So that's the total time. And then there'll be a Q&A session and discussion. And it's very important, these presentations will only take place on campus, no exceptions. And in your presentation, you can score up to 50 points. 40 is on the presentation, plus 10 is on the Q&A at the end. And initially, what I want to see in your presentation is the motivation of the design pattern and the problem it's addressing. Then your solution and why it works. So how the design pattern works and why it actually solves the problem. A little bit of code, how we can reproduce this. There's plenty of code in the book, just snippets, not too much code, just some snippets that we see how to actually address this problem. And then each book chapter also covers alternatives, meaning other approaches to solving this problem. And I want your slides to look reasonable, so there'll be a few points for the visualization. If you have more ideas on top of the book chapter, if you have some other alternatives or additional explanations, you're most welcome to add this. And you have 15 minutes for that, and then there'll be a Q&A session. And the portal will open today at 1 p.m. and sometime close next week, but I've written this in the iLearn course already when the portal will be closing. And once the portal is live, it will also show you when it's closing. So don't be late. So this is about the seminar presentations, and now we can resume to uncertainty in learning. So read that chapter next week because it's explained so well. So I felt it doesn't make sense to copy this chapter step by step into the slides, but rather we discuss something that is maybe not explained that well in the established literature. Has any of you ever dealt with a Gaussian process? A Gaussian process is a machine learning model, and it's available through scikit-learn in a quite good implementation. And the Gaussian process is a non-parametric supervised learning model. It allows you to do regression as well as classification. Now you're wondering, why is it that helpful? There's a second definition about what a Gaussian process is, but I've just taken this from Wikipedia. I'm not reading it out, but I find the definition from scikit-learn is relatively short because we don't see the advantage yet. A supervised learning model for regression or classifications, or why do we need it? The definition in Wikipedia is actually extremely good, but we'll look into this in a moment. What a Gaussian process allows you to do is, it allows you to learn a classification or a regression task, but it also gives you a confidence interval. So it also, say, if we use this for regression, what we see here in blue are our observations. So our training data. We are learning a function. For example, we are doing a mean prediction, which is some sort of interpolation. This is for regression, and I said, whenever you make a prediction in regression, it will ultimately be wrong to some extent. So it would be good to know how good or bad your prediction actually is. What we see here in orange is the 95% confidence interval. So this gives you an uncertainty measure. That means if you predict something that is still within this confidence interval, you can also change it obviously to 99% or 90%, depending on your use case. You can get an estimate of how good or how bad you are in your prediction. So if we look at this, for example, where I'm putting my mouse, this should also be in the screen share and record it. So I'm putting the mouse between the first and the second observation. We see if I'm a little bit on or off this red mean prediction, it's probably not that bad. But if I'm totally out, say totally up somewhere up here, then it's probably a super bad prediction. And this is the good thing about the Gaussian process. It learns me a function, or say a hypothesis, because in fact it uses many functions, but it learns a hypothesis. And then it also gives me an estimate of its confidence. And this is something extremely useful when you do regression, because you can also give a confidence of how good or bad you are when you're predicting. And I've used this kind of stuff, for example, in industry use cases where we needed to make a prediction. And if it was a super confident prediction, we could just automatically do it, use it as a decision. And if our system was maybe not that confident, there could still be a human intervention, ultimately making the decision, say in some procurement or some manufacturing setting. It's super confident, we're fine, we automate it, or we just use the automated decision. And if not, maybe a human should intervene based on obviously the impact and if what the consequence could be. So this is one way we have done it. Obviously, we had to set a threshold for the confidence interval and when we actually accept the automated decision or when a human would intervene. The good thing is there's a lot of theory about Gaussian processes, but you can also just use it in scikit-learn. And we'll now look a little bit at what Wikipedia says. So Wikipedia is always something to take with a grain of salt, but I like actually the definition of a Gaussian process in Wikipedia. So a Gaussian process is a so-called stochastic process. And Has any one of you ever dealt with stochastic processes? Not sure if this was in your statistics course. A stochastic process is actually a collection of random variables indexed by time or space, for example. And a Gaussian process is a stochastic process. The Gaussian processes are not just used in machine learning, they also have a background in from the field of statistics. And these Gaussian processes allow us that for a finite collection of those random variables that have a normal distribution. That means every finite linear combination of them is normally distributed. And the distribution of a Gaussian process is that joint distribution of all of those infinitely many random variables. And as such, it's a distribution over functions with a continuous domain. It's a long text, long sentence, or actually two sentences. But I felt rather than putting that definition here, I'll just show you an example of how you can actually take advantage. If you look into statistics, they use it for slightly different applications. We in machine learning would use this for predicting. And what we can use it for in the machine learning world is simply that we can get a confidence interval in addition to the hypothesis we have learned. And then you can have a measure simply of how good or how bad you are predicting. And I've used this kind of stuff to determine whether we automatically accept the decision, whether a human would intervene, maybe whether we would use a second model or something to double check the prediction. These are the kind of things you can do with such a Gaussian process, and you can use it fairly easily in scikit-learn. When you took my computer vision course, and I guess, who of you took my computer vision course last year? I guess almost all, not the exchange students, obviously. In the computer vision course, I also talked about AutoML, automated machine learning, in which I let the library pick a suitable model for me. Something I used, or something I noticed when I used the AutoSK-learn, that it surprisingly often picked a Gaussian process for a lot of my real-world problems. This doesn't mean the Gaussian process is something that is better than the others. That's just my observation. It was returned quite often as the best model in this search for specific problems. And a good thing was, on top of just training a model that worked reasonable, I also had this confidence measure. Those Gaussian processes, they are useful because we have a reliable estimate of their own uncertainty. They also work with kernels. So kernels are something you have seen in support vector machines. You can also pick a kernel. If you pick a kernel, you can incorporate your expert knowledge, because based on your domain knowledge and the domain you're working in, maybe one kernel works better than the others. So that's an advantage. But the problem with Gaussian processes is they're computationally expensive. So they're non-parametric, means we don't have a fixed number of parameters. And they need to look at actually the whole data set each time they make a prediction, at least in the implementation in scikit-learn. There are other hacks that try to avoid this. And when you have high dimensional spaces, my impression is that the Gaussian processes don't work too well in high dimensional spaces, because we have the curse of dimensionality. So they're not something that maybe work too great in high dimensional spaces, but depends again on your data set. So if you have never used Gaussian processes, give a try at them. Maybe in your AI project or something, for those who are taking it with me, if you have to predict, I don't know, spare parts or something, maybe something like this could be helpful. So maybe this is something the industrial partner would like, if you can show not just a prediction, but also a measure of your uncertainty. So these are Gaussian processes, and they have been around for quite a while. And there's now a newer approach that has become extremely popular to handling uncertainty in learning. And it's called conformal prediction. Seems to exist for more than 10 years or something, but in the last 1 or 2 years, a lot of people in the machine learning domain are fascinated by conformal prediction, because conformal prediction from its theory is super simple. It's not for free. You will still need a little bit of theory, but the theory is actually far simpler than if you try to understand a Gaussian process in detail. And this conformal prediction is something you can apply to nearly every classifier or regressor. It's sort of a higher level you put on top in order to handle uncertainty in learning. And there's also a library to do this for you, but I want to discuss the theory in greater detail with you today. Conformal prediction works for any predictive method that is of the form P of Y given X. So I want to know the probability of a label given my input. And most classifiers and regressors are of this type. And conformal prediction is something I can plug on top of these models. And it makes super little assumptions. Most machine learning models actually make some very strong assumptions about your data. And I'll check the pen here to write this down. Just looking for a pen. It doesn't seem to be any, surprisingly. Then I'll ask it. Who of you has heard about IID? So an I and an I and a D. Anyone has ever seen this? So IID means independent and identically distributed. Does that ring a bell? And this is actually an assumption about the distribution of your data that most machine learning models make, not all, but many. And IID actually means your training data, or at least the error in the training data, needs to be normally distributed. And if that's the case, your machine learning models work well. If that's not the case in the data, sometimes they don't work too well. And then you see all these hacks trying to transform data sets into some other data sets, trying to turn them into IID, but it's disputed if this actually is reasonable or not. And the good thing is about where does this IID assumption come from? Some people, they say, well, this is all 20th century statistics, and now we're in the 21st century, and we can have smarter models that don't make such assumptions anymore. That's what some people say. I have my doubts about it. I think the fact that a lot of machine learning models assume IID, there are some good reasons for it, and we have good models from the 20th century that we still keep using and probably keep using for the foreseeable future. But if there's some progress in theory, I don't mind. And this conformal prediction makes a totally different, or makes a much weaker assumption. All it assumes that my data set or the entries in my data set need to be exchangeable. Exchangeable simplified means I can just change the order of the elements in my training set. So the order doesn't matter. And this is something, it's a very weak assumption. So, it doesn't enforce a lot by doing this. The problem is if you require exchangeability, this doesn't work for time series. Because in a time series, I assume a certain order of my data points, but there are extensions of this conformal prediction for time series, which we leave out for now. So what I'm showing you now is a little bit based on a book that appeared last year. Does any of you, this book has been around actually for a long time, at least the first edition, part 1, Probabilistic Machine Learning by Murphy. Anyone read this book for studying? So it's also a book that has been out for at least 10 or 15 years. There was one book, and then Murphy offered a second edition, not just of the first book, but a second book came up as well with the advanced topics. And this appeared last year. There are quite some advanced things in it. I'm super happy with the second book, because it covers some stuff a lot of other books, like Bishop's machine learning book and other, don't cover. You don't need to buy it. There is a draft available of the whole PDF available on Murphy's website. Maybe without the final editing just before printing, but I think overall it's a good stage. I bought both books because I was curious, but I know they're quite expensive. So you can find the PDFs online. And the advanced topics book by Murphy covers conformal prediction. It actually explains it quite well. So I felt I compiled the essence here into a few slides to show you what it is. So in conformal prediction, we need to start with a heuristic of uncertainty. So we somehow need a measure to say how certain we are about a label. In a regression problem, that could be variance, this certainty or uncertainty measure. For classification, it could be softmax. Softmax, does that ring a bell? I have a footnote about softmax. So softmax is often used in neural networks because you have your output layer. Say we have a traditional neural network, could be a deep one or not, and we have the output layer for classification. We put in some data, and each output unit will give us some value. And we're not really able to assess these output values too much. What we do in a classification, at least the simplest form, is we just pick the unit that has the largest output value and we say that's the class. But when you have these data sets with like thousands of different classes, you cannot just pick the one with the largest value. Rather, maybe you pick the top 3, top 5, and then you calculate the top 3, top 5 error. So you say it's correctly classified if the label appears among the top 3 or top 5 classes. But still, these values, they don't really add up. And with softmax, you can turn them into quasi-probabilities. And softmax is shown down here. So you have a vector Z, so it's in bold. And this vector, you could imagine it's just the output values of the last layer of a neural network. So you have k many entries Z1 through Zk. It's a vector of length k. And you compute the entry or the value of each entry by taking Z at index I, and you take E to the power of the value that you have in Z so far at that position. And then you divide it, and then you do exactly the same for all entries. So you take all entries and you raise them E to the value of the entry. You sum that up for all entries, and your one entry is divided by that sum. And you keep doing that kind of calculation for every entry. So for an entry, you take E to the value of the entry, and you divide it by the sum of, and for each of them in the sum, you take E to the value. So this is softmax, and then you can sort of turn your values into probabilities, and they will eventually add up if you do it right. And the softmax score can be used as our heuristic notion. First, in this lecture, we'll look into conformal prediction in general, what it is. And later, we will apply it concretely to a classification problem and see how it works. So we could use that softmax score as our heuristic measure. And this heuristic measure is something we call a conformal score. How to calculate a conformal score exactly is something depends on your concrete problem. For now, we just say our conformal score is a heuristic. And we can calculate this for an entry and its corresponding label. And a conformal score is always a real number. And this conformal score measures how badly your output Y conforms or matches to your input X. So the greater, the worse. So actually what we mean is large values are less likely. So large conformal scores are something we rather want to avoid. So large values are bad. So we could rather see this conformal score actually as a non-conformity score. I don't know why the literature just doesn't call it directly non-conformity score, but the literature calls it the conformal score, which actually we want to avoid large values. So this is the first part. And we now define a few more parts, and then we have defined conformal prediction, and then we'll apply this to a concrete classification problem. Now, we apply this score to a so-called calibration set. And we have n labeled examples that was not used to train the model. So we have our training set, but from the training set, we leave a few elements aside and don't train the model on those. And for those that we have left, we calculate our calibration set. And the calibration set, what it means is it's called S, and it's actually for our n many calibration examples that we didn't use for training. We just calculate their conformal scores, because this is just from before. We have S and Y, and we want to see how they actually conform to each other. We have the conformal scores, and we put them into our conformal, in our calibration set. There's now a little bit more text. There's a footnote. What we're doing is actually called a split conformal prediction. We needed to take some data aside that we couldn't use for training. There are other approaches in conformal prediction, more advanced ones, that allow us to address this issue if we don't have enough training data. But that's just a detail, because you would use a leave one out type procedure, but that doesn't matter for now. For now, we just assume we have n additional examples which we didn't use for training, and they're enough. Now, the book says something: the user specifies a confidence threshold. User would mean you as a data scientist, for example, not the end user. So the user who uses the conformal prediction framework, which is the data scientist. And you define this confidence threshold. It's alpha, for example, 0.1, but depends on your use case. And then you compute the 1 minus alpha quantile. So the 0.9 quantile, which we call Q hat, of our calibration set. And again, the book makes some further details. Because we have a limited size of S, this 1 minus alpha is maybe not too great. You could calculate 1 minus alpha in a far more sophisticated way, which seems to be statistically more accurate. It's something n plus 1 times 1 minus alpha, and you take the ceiling of this product and you divide it by n. That's something proposed and argued in the book, but we just keep it simple and say 1 minus alpha. We don't care if the data set is too small, at least in the first attempt. Now we have taken these n examples for the calibration set. And now we have one more example for which we are predicting. So we have a test input. This is the next one on which we are predicting. This is X with the index n plus 1, because we had n many for a conformal prediction, at least to calculate a calibration set. And now we take the next one for a prediction. And we want to know which label is the right one. That's ultimately the goal, but there can be multiple labels. So we need to calculate a prediction set. And this prediction set of our example, so prediction set is called T of our example, is calculated the following. I calculate these conformity score, or the conformity score for my example, with one label, but I have all possible labels. So this is a set. That means I'm going through all the possible or all labels I have available. Could be 5 output labels, could be 1,000, depending on the use case. So all possible labels, because I don't know the right one ultimately. I could predict and say, this is the one I'm predicting, but we don't want to do this because we want to get a distribution of the ones that are, say, most reasonable. So I'm calculating this prediction score of the test example and a label, and I'm doing this for all the labels, and I only keep the labels where this conformity score is less than or equal to Q hat. And remember, Q hat, I calculated by saying 1 minus alpha. And what this actually means is I include all the outputs that are reasonable or plausible given the input. So the ones for which I'm actually confident. Now I have an example to visualize what all of this actually means. We'll start with the left one. It's a classification problem. I've put in, it's about images. We'll later see this concrete example again and the image. And I'm predicting the whole output layer. And I'm applying softmax to these predictions. And what I see here is the cumulative softmax output. So fox, squirrel, it's one class. This is actually the most likely one, the one for which I have the largest softmax value, which is in the prediction set. So it's a reasonable one, which satisfied this inequality here. Then I have the gray fox, and I also put it in, and then the cumulative softmax output grows, but it just grows a bit. So we see from here, fox squirrel is the most reasonable one. And then this cumulative one goes up a bit for gray fox, then for bucket, then for rain barrel. And these blue ones are the ones that still satisfy this inequality, and the others don't. So mammoth, polecat, or marmot, polecat, and weasel, they are possible labels, but I see from the softmax, I'm just adding very little to the cumulative softmax output. And these are the ones that don't satisfy this inequality. So my prediction set, in which I have the labels that are accurate, so the inequality from before, or the labels not maybe accurate, but plausible, are 4 ones. Maybe this example helps a little bit to understand these equations from before. This is for classification, and for regression, we can do the same. We have a regression in a data set. In our prediction set, at least the blue one is, so we see we have somewhere in between the regression, the quantile regression, and outside we have these boundaries of the prediction set, and those are possible Y values that are still plausible. So this looks a little bit like the Gaussian process before, but it's a completely different approach. And what it gives me is some here it's not really a confidence interval, because this is what the Gaussian process does, but it's some measure of confidence which are still plausible Y values. But the regression plot is probably a little bit more difficult to understand than the one for classification. A little bit more theory, and then we go through one more example for classification. Now the book shows something like this, and the book says, remarkably, one can show the following general result. I don't read this out for now, but what we have in here is our 1 minus alpha from before. And now what we have here is a P star, and P star is actually the true distribution of our examples 1 to n plus 1, so the 1 to n from before for conformal prediction plus number n plus 1. And the what this shows us is the probability or the true distribution where we say that this label is actually part of T, and T is our prediction set. And this probability is less than or equal to 1 minus alpha plus 1 divided by n plus 1. This is how to prove this is shown in the book. We're not proving it here because I think it's already a tough start. But what this actually means is, and there's a new term that you will come across because later I'll show you how to use conformal prediction easily as a data scientist. If you ever come across the term coverage level, 1 minus alpha, this is exactly the coverage level and how it's defined. And there's a little bit more text, but we'll skip this text now in the first iteration. Once you're revising this, and maybe take a look at the book, take a look at another slide as a further explanation of this inequality. Now we'll start applying this to classification and see what it's actually useful for. Because so far we've just looked at the general equations that we can use for both classification, regression. We said we're dealing with a conformal score, which is our non-conformity measure, actually. But we always said we use some conformal score. Now we'll use a concrete one. And then we see how this works for classification. We are now working in a multi-class classification setting. We're using, again, the softmax score on all the possible classes that we are predicting. So it's very important. This not only works for a neural network, but with a neural network, it's just easy to imagine that we have this output layer, but can be applied to all these other models where simply you have this probability of the label given the data. And our conformal score, which is actually our non-conformity measure, we say it's 1 minus f of x. So f of x is the softmax score for a specific class, because we have class y, and there could be multiple classes. What I'm doing is I'm putting x into my function f, which is the hypothesis or the machine learning model, and I say, well, 1 minus this, and I put a y down here, which just means if I have multiple classes, y will just give me the real value for this class y and not the other classes. Because again, for the neural network, which is easy to imagine, I have multiple output units. And why is it 1 minus this? Because if, say, f of x is very, very small, or f of x for element y is very, very small, that's actually a very bad prediction. So it's a very low softmax score, and then it's a high score, and we said this score is actually a non-conformity measure, so it's something unlikely. While if I have a very good softmax score, then 1 minus this will reduce the value substantially under 1, closer towards 0. And then it's more likely. So that's the idea why I say 1 minus this. Then we calculate the threshold Q hat as before, which was 1 minus this alpha, where alpha could be, for example, 0.1. And then we define our prediction set as following. The prediction set is I take all the labels where the softmax prediction of the label is greater than or equal to 1 minus Q hat. This 1 minus is a consequence of how you calculate the quantile, as well as because we said here 1 minus this. So what we are putting in the prediction set is we take the set of all class labels that are above this specified threshold. And now we have a classification problem that becomes increasingly more complex. A very simple one is the first image, where I just have, this fox squirrel, and I put it into some classifier, say some neural network, and it only gives me one class, which is fox squirrel, and it's 0.99. There are obviously other output nodes in that neural network, but simply the fox squirrel is so likely that the other classes are just falling out from this inequality here, because this one is simply so likely. Now we have a more complex image in the second one where we have the fox squirrel, but there are more classes that actually still fall into the prediction set, like gray fox, bucket, rain barrel. They are less likely, but we see they are still somewhat more reasonable than before. And then it's up to us as a data scientist in our use case, how we handle this. If we change the threshold, if we say, well, if the conformity measure is a certain value, or say not the conformity measure, maybe the softmax score, if it falls in there and reaches a certain threshold, I'm okay with it. Maybe human intervention, again, depending on the use case and its severity of the impact. And we have another image here, which is definitely doesn't look like a fox squirrel. It's more likely a marmot. And we see, well, there are multiple classes. Fox squirrel is one of the possible ones, but actually not the most likely one. So this is how we can describe conformal prediction in a couple of lines, or a couple of slides. When you start using this, and you should look into it, because in a lot of your real world use cases, you're dealing with uncertainty. And how to handle the uncertainty, there are different models. I said there's a Gaussian process, which has pros and cons. And conformal prediction is something you can plug on top of nearly every supervised learning model, at least the ones that work on the probability of the label given the input data. And you don't need to code this from scratch. There's a very good library called MAPI. It's the Model Agnostic Prediction Interval Estimator. Has anyone ever seen this library? Only see disagreements. This one allows you to do conformal prediction plus actually other things, how to control risks of more complex tasks. So it's not just for conformal prediction, it's actually also for calibration, which is the next approach we'll look at. And you can easily use this. So you see, well, you're using some regressor, some classifier, because here you're putting in your regressor or your classifier, whether that's a decision tree, a support vector machine, logistic regression, a neural network, it's up to you. You can plug it in. There are different methods you can, or different scoring methods you can put in. There are different thresholds you can define. You can even combine this with cross-validation. So it's super easy to plug conformal prediction in, because you just use your model that you have trained already. And like this, you can assess it, or you can address it from a conformal prediction approach. And you don't need to constrain yourself to a single model, like a Gaussian process, or lots of heavy theory, or lots of assumptions about the data, because here the assumption was simply exchangeable, which again doesn't work for time series. There's also one, because I said this could be interesting also to try out this year already for the students who are taking my AI project. There's one group that is working on predicting demand of spare parts. I don't know if someone is here from this group, then online. And if you're dealing with time series, there are also extensions of this framework. But most of you are probably not using this on time series in your first attempt. So give a shot at this library, will make your life easier. And now there is another approach. So conformal prediction is one way to increase or to quantify the uncertainty. And there's another approach that we call model calibration. And what is model calibration? It's also something that has become more popular in the last few years. And we look at, for now, binary calibration. Binary calibration allows us to transform a score given by a machine learning model that is not a probability, and we convert it into a probability. And again, algorithms that are used to do calibration, they can be interpreted as an estimator of a confidence level. Because if your model predicts some numeric values, they're not probabilities. If you can convert them into probabilities, it's some way of estimating confidence or unconfidence. I have an example here of how to imagine this. What this figure shows is we have on the x-axis our confidence score, and on the left we have or on the y-axis we have an accuracy. And in blue we have scores from some algorithm. Could be a neural network, could be, I don't know, a logistic regression, whatever. And we see if they make predictions, we sometimes have high accuracy, but actually low confidence. Something we don't want, or we maybe have low accuracy, but high confidence, sometimes okay. But if you make a high accuracy, but you have a low confidence, this is uncalibrated and can lead to lots of problems. So if we calibrate our scores, they would more or less fall onto this diagonal, and calibrating the scores will give us a much better estimate of the confidence, and it's something we want to do. How to do calibration, I spare you another 5 slides only with equations, as we did for the conformal prediction. The MAPI library also helps you with calibration. Now you could think, well, calibration is really cool. Is this being used in practice? And there was a paper from a few years ago that I personally found quite surprising. And those researchers, they addressed this whole progress in deep learning in the last 20 years. Now we have ever larger deep neural networks, and they give us better prediction results, at least we believe so. But it turns out that the neural networks we use nowadays, these deep neural networks, they're actually far worse calibrated than the old neural networks that were trained in the past that are smaller. So they actually were more certain. Now we could think, well, let's make all those neural networks calibrated, and then it's all good. And this whole topic of conformal prediction is something I heard about it years ago, but there's one of my LinkedIn contacts, Valery, and he somehow seems to be the ultimate deal in calibration, in conformal prediction. He did his whole PhD about this. So hi, Valery, in case you hear the recording, because I'll definitely tag you on LinkedIn when I post this video in YouTube. And because he posted about this all the time, I also started investigating conformal prediction more and learned the theory and understood the importance of it. And so if you want to follow the expert worldwide, probably in conformal prediction or model calibration, that's probably Valery on LinkedIn. And he also looked into this, and he posted a while back. It was not his paper, but someone else who studied various methods of how to calibrate neural networks. There are multiple methods, but it turns out that if you calibrate your neural networks that are uncalibrated, this not only leads to positive effects, also to negative effects. And a negative effect that was discovered or in a study was that actually when you increase, say you have a binary task and you take a model, especially modern neural networks for binary classification that are not well calibrated, and you calibrate them, this diminishes the fact that you can distinguish between the two classes in the output. So it's maybe calibrated, maybe this gets better, but you're less able to distinguish between the two classes. So this is an active research topic, maybe on how to address that issue then. I also keep following the progress in conformal prediction, also use it in some projects sometimes, as well as calibration. And if you want to see the latest papers on these topics, follow Valeri. I think this topic will gain more importance because now if you look into politics, there are all these fears about an out of control AI and that you cannot or couldn't trust the AI, at least that's what the politicians say, and that, you know, the end is near, which I totally disagree with. But because of all these additional compliance requirements now coming with the AI Act, probably those kind of things will gain more importance in the coming years. Also, when you do a job, we can argue whether the AI Act is useful or not. I think it's not useful to a large extent, but it's becoming a reality. So your employer needs to certify and needs to follow these rules, and probably uncertainty or certainty estimation in machine learning is something that will be more demanded in the coming years. That's why I've put it this year in the course, because I just saw all these posts on LinkedIn exploding in the last, 9 months. And that's why I felt I add this here. Obviously, we could spend a whole semester on it, but that's not the purpose of the big data course. It's a very broad course, and this week we're looking into this. So I've given you now plenty of references to investigate this more in case you want to learn it more. Could be helpful also for finding a job or at least getting a better pay than others. So maybe next year I will also add noise in labels. This was discussed today by some of you who today gave in the AI project a quick presentation about noise in labels. I think it was you and you exactly. This is something that I already had on my agenda for the next year, but this year I'm doing the uncertainty in learning for the first time, so I felt it shouldn't be too much theory in the first attempt. The ML Ops was your homework to read last week, and it's certainly very helpful for picking your seminar topic. And now we still got half an hour to look into this whole world of natural language processing and how it's being changed, the hot topic, transformers and ChatGPT. Because there is a deep learning course, but I think the deep learning course is more like how to build your own neural networks. I don't think there's too much time at the end for transformers. The NLP course is earlier in your studies. It's more about syntax, statistics, and lots of other things. So I felt a good point to add this in this degree program is in the big data course. And I'll start talking today about big data for NLP. Our goal is we make it to transformers in this lecture. Maybe not today, maybe next time. We need a few foundations, including embeddings. Later in this semester, so you see we're coming somewhat towards the end of the lecture part. There is more than just your seminar presentations at the end of the term. We will probably be having now 3 guest lectures in the next few weeks, but I'll announce them in time. And for the guest lectures, I would definitely expect you to be on site, not just online. One guest lecture will probably be online, so we'll be meeting online, but 2 of them will probably be on campus. And at least one of those, maybe 2, will cover transformers or something like this and how companies use this for real world problems. So because lots of companies have recently got in touch and they want to give guest lectures because they're all desperately looking for AI experts. And now I have to limit the number of guest lectures because probably 3 guest lectures is enough at some point, but I'll inform you. So when we deal with text in machine learning models, we somehow need to convert text into a format that our machine learning models can work with. And this may be something, I don't know, you have seen in the NLP course taught by Professor Garman. I don't know if he discussed this kind of stuff. In the past, I taught half of the NLP course, but now he's teaching it completely on his own. Somehow we need to, and this is something I discussed in that time in the NLP course. I don't know, did he discuss this? Because you've taken his course, how to convert text into numbers so the computer can deal with them, or machine learning models. Anyone heard about one-hot coding or something like this? Okay, in a machine learning course, yeah. And so somehow we need to represent text as numbers. The simplest thing could be that each unique word somehow gets an integer. So we have the first unique word, for example, it's 1, then hello is 2, then computer is 3, and so forth. This is one approach. We'll soon look at if it works or not. And then there are increasingly more complex approaches. And word embeddings are now the hot topic, so we'll also focus on it. But first of all, does it make sense to encode each word with a unique number? To me, this is first of all arbitrary. Why is the one word a 1 and the other a 5? It's also very difficult to interpret, and you're creating arbitrary distances between words. So you have two words, maybe index 1 and 1000, so you have a huge distance, and you have two other words where you have index 10 and 20, so the difference is much less. And if you just enumerate unique words with a new index, you're creating arbitrary distances, and your machine learning model will definitely be garbage in, garbage out. It will still learn some pattern, but I don't think it will work any reasonable. And it's all very difficult to interpret, and probably based on luck, like which was the first word and then the second, and maybe it works, maybe not. So don't do that. Then one-hot encoding is something that has been used for many years. You would say my text has, for example, 5 unique words, or a certain, you would just count a number of unique words in your text. There are small text where we say we have 5 words, but obviously this can be applied to more words. And then you would now represent a word as a vector. And in the vector, you would have for each unique word a position. So we have vectors, or the vectors here are row vectors. The word the would be the last index. You would say a 1 and all the others 0. For cat, you could say it's the first index. For set, or whatever this is, yeah, the cat set, it's index 4 and so forth. So you would just go through your unique words. Say you have 5,000 unique words in your text, and then you would map each word to a 5,000 dimensional space, and you would have all values 0, except that one entry that represents your word you would put into 1. And then you have a text, and your text would finally be a matrix, because you have multiple words after each other, and each word is represented by a vector. This avoids some of the problems from before, but creates new problems. It's very inefficient because you waste a lot of space, because your vectors will all be 0 except one element. And this leads to super sparse vectors eventually, especially if you maybe have a few 100,000 unique words in your text. And this will ultimately lead to lots of memory usage. You can address the memory usage actually quite okay, but it will lead to the curse of dimensionality again, high dimensional data sets, and it's very difficult to learn a pattern in them. So was used, sometimes still used, but things have changed. At least they have an advantage. You can calculate them super easy. Just calculate very big vectors, but calculating them is easy. What you can do instead is you can use embeddings, and embeddings are a very dense representation. And an embedding has a certain number of dimensions. Here, the embedding would be, no, it's a little bit small, this figure. For example, 4 dimensions. And you're not just putting in zeros and ones, but rather numeric values. And while now this is only 4 instead of 5 dimensions before, in practice, the scale, say you have maybe tens of thousands of unique words, and then maybe your embedding has a dimension of a few hundred entries, which is substantially less. And with these embeddings, they are dense representations. How do you find these representations? Well, you learn them with machine learning, for example, with a neural network. So you don't have to encode these embeddings by hand. And if you learn them well, it can be shown empirically that similar words, not same words, but similar words, have a similar encoding. And for example, here we have multiple vectors, and there are 4 dimensions each vector. So we see a cat and a dog. They have some things in common, but other things or some entries are quite different to, for example, rabbit or cheetah. Comparing 4-dimensional entries is a bit difficult, but you can also try to plot this in 2D. And so you can map. So what this was done here, this was a 300 dimension. I saw you, just wait a second. This was a 300 dimensional embeddings that were learned, and then this was compressed into 2D, so using the 2 principal components, and then plotted. And we see, well, cheetah and lion and tiger, they are quite close, but hamster is quite off. Mouse and rat, they are somehow interlinked. So they are not too far away. Monkey is far more off. Yes, what's your question?
This is the data set made because I don't see a machine learning program being able to determine if something is fluffy or.
In this case, this would just be an interpretation of what these 3 or these 4 dimensions would mean. This is just an example. So the machine learning model would not learn this. No, it's just dimensions. This was probably somehow determined by an expert, or they maybe plotted each dimension separately, and the humans could somehow identify that this could be fluffy or domesticated, but the model obviously doesn't learn this. It's probably just an interpretation or explanation added by humans. But you can just put this in 2D, and then you can see how close they are. And the good thing is these embeddings, you can simply learn from very large text data sets of how these words appear with each other. You don't have to define what similar words, but only how they correlate and how they appear together. And this can be learned with a neural network. There are typically 2 approaches. One is the back of words approach. The other one is the skip crumbs approach. This is offered by machine learning libraries like Keras and others. So one of the early stages when you process text nowadays with neural networks is you would first learn embeddings, or maybe if you have a pre-trained model, this one was already trained on enormous data sets, so you already have your embeddings learned and you can use them, or maybe have to refine the embeddings a little bit if you have extra words or a somewhat different distribution in your data. And you can fully autonomously learn these embeddings. So you as a human, you don't need to craft them. And then what you have is a dense representation, maybe a few hundred entries per vector, rather than hundreds of thousands. And these embeddings, they're compressed. They actually also represent meaning or similarity. So they're something quite useful. And those are then used, or those vector representations is then what is put into the machine learning model for your concrete task, like classification, text generation, and so forth. When I started with this course a month ago, I said there is this new deep learning book by Bishop and his son Bishop, which is the same style as this previous Bishop book from 17 years before or whatever. This deep learning book covers how to learn embeddings very well. So in case you're curious about the details, look into this. But this is something that would maybe be discussed in some advanced NLP course. So we don't do this here in the big data course. Just in case you're curious, I read this whole new Bishop book during the Christmas break and found that part super helpful. So I'm referring you to the book. Historically, there was a somewhat different approach for how to calculate these vectors, which wasn't called embeddings. It was called TF-IDF. TF-IDF is also a scoring or real values for these vectors. And TF-IDF means term frequency, inverse document frequency. What it tries to balance is how often words appear, not just in a single document, but throughout all the documents. And then you can try to balance this out and give weight, for example, to rare words that are less common, something like this. But this TF-IDF, I would not say it's obsolete, but probably less important nowadays because we now have embeddings at hand. So this TF-IDF is probably used less than it was used in the past. Mainly came from this whole information retrieval subdomain within AI. But in the last few years, I see this declining. So there are some pros and cons of both approaches. With word embeddings, obviously you need to invest a lot of computing time because you need to learn them, which is quite heavy. With TF-IDF, these are just simple fractions that you need to calculate. So that's probably far cheaper than training a huge neural network. So there are pros and cons, but nowadays you would probably just use a huge pre-trained model in most of your cases, and then you already have also pre-trained the embeddings, and then you're okay. I saw we have a hand raised. Yes.
Yeah, I'm not sure if it's going to be explained further in detail later, but how do we specifically group similar words together? Like, do we already have them pre-labeled and pre-classified to train a model?
You don't need to do this. It's all found by the model, simply how words appear together and in which context. Simply learn from large data sets, and that's why you would not retrain or train the embeddings from scratch on your small data set, rather from very large text corpora. So you don't need to define that.
So for example, if similar words appear together in a singular text, then they seem to be linked.
Yes, or simply the context, for example, depending, I don't know, maybe rat and mouse would appear often together in text, that people have problems with this in their house or in their garden or something, and they need to put poison. And then the model would just learn that somehow these are quite similar in terms of their meaning.
Okay, thank you.
I still have a few minutes. 4 years ago, a super nice video appeared on YouTube by DeepMind, this Google subsidiary working on major advances in AI. And that video covered super well how neural networks can process sequences. So using recurrent neural networks. This is something you would need if you want a neural network, or at that time, at least, if you wanted a neural network to work on text, because a text is somehow a sequence of words. And this video was presented about 4 years ago by Marta. Marta was one of my fellow students during our master's, and this video was prepared extremely well. So if you're curious about the state of the art until 2020, take a look at it. I think it's excellent, it's terrific. But a lot has changed in the last 4 years. That was just at the beginning, and that could not be anticipated what it would ultimately lead to, because a paper appeared in 2017. Attention is all you need. Who has read the paper? I see some people recognizing it. Probably the most famous paper in the last 10 years now. And this paper actually proposed the transformer architecture. And the transformer architecture uses the so-called attention mechanism. And that one tries to find out how tokens correlate. What's a token? Token can be part of a word or a small word or some special character. And finding out or learning how these tokens correlate, how they appear together, is something that has been done in assistant systems and machine learning and natural language processing for decades. For example, using hidden Markov models as one approach that was quite popular until a few years ago, because most of these systems, they tackle how tokens appear together, and they maybe one word or one token appears always with the other or in some distance. And the question is how you learn this. And what you're doing effectively is you want to learn a high dimensional distribution of tokens. Hidden Markov models is something that was used for quite a while, probably starting the 80s or 90s. Then all this stuff that Marta talked about, recurrent neural networks, they were probably already proposed in the 80s and 90s. And then also LSTMs, long short-term memories. And then all of this became more popular again since 2006, 2007, when this deep learning boom started slowly. And then those can learn these distributions, but then this transformer architecture was proposed. And people talked about this in 2020, but probably just it became more popular shortly after Marta's talk, because in 2020, GPT-3 appeared sometime, I think in spring. I remember I had just started here in February 2020, and then there was COVID and the university was closed and all of this. But somehow people talked about GPT-3, the predecessor of ChatGPT. We'll also talk about ChatGPT in this chapter. And GPT-3 stands for Generative Pre-trained Transformer. So T, transformer, based on this paper. It's generative, it generates new things, not just classifications. And it's pre-trained, means it was trained on huge amounts of data. And I can either use it or fine-tune it and then use it. And this was proposed, in May 2020, and is based internally on a transformer. I often get asked, it's not the same with ChatGPT. Why does it always generate different outputs, and why does it each time give me something different? That's not a bug, that's a feature, because it's an autoregressive model where you exactly want this kind of behavior, but there are some other language models that are just deterministic. If you want them, you can make all of them deterministic quite easily, but it's something you don't want. You just want the diversity and not always generate the same text. And GPT-3 has 175 billion parameters. A few years before, they published a paper about GPT-2, which people then tried to rebuild, and then GPT-3 appeared, and the paper or the technical report still provided some insights, and they had 175 billion parameters trained on hundreds of billions of words. And it was determined that it would take 355 years to train GPT-3 on a Tesla V100, the fastest GPU on the market at that time, and would cost $4.6 million to train one instance on the lowest cost GPU cloud provider. You do this 4 years later after COVID, the war, and in Germany, and probably you'll be spending 10 times this now if you want to train. But that was estimated, and it was noticed very quickly that this could not only generate simple texts, but also code. And I started to try this out, and GPT-3 had a far more complex interface. I'll talk now about GPT-3 because in the next lecture, I'll say what's different in ChatGPT, because there's quite some stuff, but you could say, well, complete me this text. Plus, the user interface provided all these buttons here, like the temperature, like creativity, or frequency penalty, maybe a penalty that when tokens appear too often, response length. All of this has disappeared from the user interface with ChatGPT because most people weren't able to use this. This was just too complex. But some newspapers used it. It was in the news, but then somehow this hype disappeared again at that time. And it also had to do probably with COVID and much more essential needs that people had. Plus, the user interface was too complex. And you could also use this to answer questions. Maybe the type or the way how you had to write your prompts was a bit more complex than with ChatGPT, but it worked okay. And you could correct the grammar of texts. You could improve Python code. One of my friends, he was starting his startup at that time, and he didn't know much about JavaScript. So he just, let GPT-3 generate a lot of his JavaScript, and then he improved it manually, and it worked. And you could use an API access at that time. And then my wife didn't like this thing too much because we tested it then during COVID. And I said, hello, I'm Patrick. I live in Regensburg. And then my wife is, and then completed. And my wife is not called Susan. She doesn't work in a bank. And our children have different names. And they're not students, and they don't live in London. So my wife said, oh, this is, bullshit. I don't like this tool. But obviously, the tool cannot know. I provided 2 little insights. And in the next lecture, so in 2 weeks, I will talk about Hugging Face and then ChatGPT, a little bit more about the theory behind it. And I want to discuss next time with you how you use ChatGPT and why I see it as a huge opportunity also in education, and why I support students using this to partially write their thesis, why I think this is actually helpful given certain constraints. We'll do this next time, and then next time we'll also talk a bit about quantum computing. So maybe I finish the content next time already. So in 2 weeks, maybe we need 1 more lecture. But then in May, we anyway have a couple of guest lectures. And in addition, or then in the second half of the term, you would also be working on your seminar presentation. So make sure you pick a topic quickly. I also sent you something like this in iLearn a few days ago, that this would open, and it will open in 3 minutes. So I wish you a good lunchtime, and make sure you pick your design pattern very quickly. See you in 2 weeks.